Right. Today we're going to be looking at the derivative, which is kind of the foundation for half of calculus. We've seen in class the difference quotient used on the interval a to a plus h. And in this case, this is kind of like the same idea, except for instead of a, they're using the variable x. Okay? So this is telling us what is the average slope between the point x and the point x plus h. And then by taking the limit as h goes to 0, what we're saying is let that secant line become a narrower and narrower window. Okay. It winds up being the slope of the tangent line. And if we use x as a variable instead of a as in a numeric value, what winds up happening is we create a function that models the slope. For example, using these two graphs here below, I've got a function here. We'll call this f of x. And the idea is that we're going to take 2 points, a point at x and a point at h units further, and we're going to ask the question, what is the slope between those 2 points? And we are going to let h shrink in value, which means this point moves closer and closer to x at that location right there. And when all is said and done, what winds up happening is if we let h approach this all the way until they're on the exact same location, we wind up getting a line that is tangent to the graph. Tangent line. And if we were to evaluate this at a specific point, we would get a slope. For example, this slope has a tangent line of, I don't know, we're going to say m equals 9, not 9, 0.9. Or we could have a tangent line right here, which has a slope of 0, or we could have a tangent line right here, which has a slope of -3, we'll say. And the function that models that slope 0.9, 0, -3. The function that models the slope is your derivative. And we're going to be doing a lot of work in calculus class involving the derivative. So this is the formal definition of the derivative. It's a limiting process on the difference quotient. Okay? The derivative is the function that models slope. There are other definitions that exist for the derivative. The two that we're going to use most commonly in class is the one shown here. In fact, I'm going to put a box around this and write formal definition of derivative. Okay. And that's the vocab I use in my class. If we replace x with a, we're going to get f prime of a, and we get the same expression. The difference is this actually gives you a value at a point. So this limit expression would give you the 0.9 or the 0, the -3, whereas this derivative expression actually gives you an equation. The equation is oftentimes what we're after. So you'll see the difference as we move forward, but they're very closely related. This is a secondary definition that I use. We'll talk more about that when it pops up, but there's more than just these two definitions for finding the derivative. There are lots of ways we refer to the derivative. The most common ones that I'll use in class are f prime of x or y prime. So that little tick mark refers to prime. And then sometimes I'll refer to things as dy dx. This is called NIS notation, named after one of the inventors of calculus. This is, I call prime notation, and I'm not sure, I don't know if this is the one that Newton invented. I think he did something else, but this means the derivative of f with respect to x, and this is another thing, take the derivative of y with respect to x. Okay. Those are all notations. I almost never use these two notations, but they're there. Something that we'll want for our notes is a tangent line equation, and this is another thing that's going to pop up often in calculus class. So f of x can be approximated by the tangent line. So what we're going to do is we're going to create a tangent line equation that we use to estimate the function. For example, there's an equation for this red dotted line, and if I evaluate that function right here, it's going to approximate the value of the green line. Okay. The further away I get from that point of tangency, the worse it gets at approximating in general. But the tangent line equation is derived closely from the point slope form of lines. And this will get used and thrown around several times in the first half of the year. But this is the equivalent of, if we wanted to think about this in a more familiar form to some of us, this is a modified point slope form, where if you know the slope and you know the point, you can create a line equation. Okay. Here we use function notation, so y1 is what is the y coordinate at our tangent center. M is our slope, what is the slope at our tangent center. And then x1 is what is our center location, what is the value of c. Or sometimes people use the letter A, so A and C. And I know a lot of this is coming across as a little bit fuzzy. We're putting it out there for you to see. On the next page, we're actually going to execute on what it all means. All right, so there's a lot wrapped into example 1 here, and so I'm going to break it down into several steps. And depending on the nature of the question, sometimes we see all of these steps, sometimes we see a little bit of it. But most often, one of the first things that you're asked to do is find the derivative. Find the derivative, or find the derivative function. And the formal definition of finding the derivative function says the limit as h goes to 0 of f of x plus h minus f of x over h. This is our f prime of x. So this is what we're going to do. We're going to do it to this function to find f prime of x. So the limit as h goes to 0 of f of x plus h would be 3 times x plus h minus 2 minus f of x minus f of x all over h. And this is like the average rate of change that we did earlier in the unit. We want to simplify this out to see if we can cancel that h from the denominator, because we can't plug 0 in for h. That would cause a divide by 0 error. So if I were to clean up the numerator, I'd get 3x plus 3h minus 2 minus 3x plus 2 all over h. And I would see things start to cancel. I notice the 3x cancels with the negative 3x. The negative 2 cancels with the positive 2, and we're left with the expression 3h over h, and the h's cancel. And now if I plug 0 in for h, it doesn't matter because there's no h's, and the limit evaluates to the number 3. Or we could say 3 is equal to f prime of x. This means that anywhere on the function f the slope of that function will be 3. And that makes sense because we have a line here, a line of slope 3. Like everywhere on that line, doesn't matter where we're at, the slope will always be 3. Okay. So now they're asking, well, find the slope at -3. Well, they're asking, well, what is f prime of -3? And, well, we know the slope is always going to be 3. So f prime of -3 is 3. F prime of anything is 3. So what this is saying is down here at -3, the slope of that tangent line is 3. M tan is 3. Now we're going to use this information to write a tangent line equation. What is the equation of this red tangent line? Well, as I said before, this will pop up often. Writing the function can be approximated by the tangent line, which is f of the center plus f prime of the center times x minus the center. Well, in this case, we're centering it at -3. So we'd be writing the expression f of -3 plus f prime of -3 times x minus -3. Well, f prime of -3 we know is an answer of 3. Two negatives become a positive. And then this number right here, we need to figure out what that is. This is what is the y coordinate when x is -3. And we can look at our function. When x is -3, y will be 3 times -3 minus 2, which is -11. So, believe it or not, this line is the equation of that red line, which is tangent to the green line. And since they're both lines and they're laying on top of each other, if we cleaned this equation up, we probably would get the exact same equation as this, because this is a line. But in future examples, when we have nonlinear functions, then that's not going to be the case. Our tangent line will wind up being a line, whereas our function was not. So there was a lot wrapped into this problem. I'm going to do a quick review so that you can think through this. First, we found the derivative of the function. Now, this was a limiting process where we expanded and canceled everything that we could, and we wound up with a very basic derivative function. Usually there's still an x behind, but in this case there was not. This is going to be a big part of the start of problems, and we're going to eventually develop shorter methods for doing this. This is kind of the longer way for now, but we'll get shorter ways. Then once we knew the slope of the function, or the slope generator, we could ask the question, what is the slope at a specific point? And that was this. And then now we know the slope at a specific point, we can say, well, what's the equation of the line tangent to that point? Well, the line tangent to that point follows this form. Okay? And this form is quite large, and I will use it. It'll pop up many times throughout the year. All right, in this example, we're going to do a very similar thing. I'm going to do some of it off camera, but I will show all the work here, but periodically I'll have you pause it to play catch up. The first thing that we need to do is we need to find the derivative. So we write down the limit definition of the derivative, and then we evaluate the derivative expression using x squared minus 5 as our function. So what that looks like is x plus h goes in for the variable, and then x goes in for the variable. From here we need to expand this all out and cancel terms that cancel. So I'm going to do that off camera. Alright, so I foiled the quadratic and I distributed the negative, and then x squareds cancel, 5's cancel, and we're left with 2xh plus h squared on top. There's an h in all three terms, so I factor the h out of the top and then cancel with the denominator, and I'm left with the limit as h goes to 0 of 2x plus h. And if I let h be 0 in this case, there is no divide by 0 error that comes up, so we are good. We now have the slope predicting function for this quadratic. If I want to know what is the slope at the point -2, and all I would have to do is plug in -2, and I get an answer of -4. If I want to know what is the slope at 1, what is the slope at 1? Well, all I have to do is plug 1 in for x, and I get an answer of 2. Okay? I'm going to sketch a graph over here so that you can kind of picture what's going on. We have x squared minus 5 is a parabola that is shifted down 5 units. And the first thing that we asked is, what is the slope at -2? Here at -2, the slope of the graph we found was equaling -4. Here asks, what is the slope at 1? So this is like saying over here at 1, what is the slope of the graph there? It's a terrible, not straight line. The slope of the function at 1 is 2. So this has a slope of 2. And now what we're going to do is we're going to create two tangent line equations. One for this first red line and one for this second red line. So the general form of tangent lines, f of x can be approximated by the tangent line, which is f of the center plus f prime of the center times x minus the center. Write it down every time. Hammer that into your head. That's going to be something that we are doing very often. In the first case, our first center that they asked was at -2. So that tangent line equation, which I'll call line 1, is f of -2 is -1. F prime of -2 is -4. And then x minus -2 looks like that. So that's for line 1. That's the equation of this left line. Now we're going to do it for line 2, where our center is at, in this case our center is at 1. So I will call that line 2, L sub 2 of x. Well, what is our f of our center? That'd be what is f of 1, and they tell us f of 1 is -4. What is our slope? What is our slope at 1? Well, our slope at 1 is 2. So our slope at 1 is 2. And then x minus our center is 1. So we were pulling lots of numbers from all over the page, but in the end we came up with two line equations. And this was for the line tangent to the point 1 comma negative 4. And this one was for, it's like my red pen's starting to die, tangent to the point negative 2 comma negative 1. Okay. So in calculus, we're going to be exploring tangent lines and the slope of tangent lines and what that means in context. We're going to do some more examples like this in the next video to wrap up these notes, but this is already a rather lengthy video, so I'll leave that for the day. Thanks for watching and have a great day.